In the past 2 weeks, we have been mostly studying social networks from two different levels. The first level is the network level. We used, for example, visualization to visually inspect networks. We used measures such as density, such as average length path or diameter, and many others to characterize networks at a very high level. In the meantime, the second level we studied social networks, we focused on specific nodes in the networks. For example, the degree of a node, between the centrality of a node, and many other ways to characterize a node in a network mathematically. And in this week, we're going to dive into a level that's in between. So what's between a whole network and its individuals, and what's the way for us to kind of study substructures in a network that does not only cover one level, such as a node level or a whole network level, but trying to understand some kind of substructures, some kind of groups, components, cliques that in between. And this is especially important, I think, in social network analysis because many times how a network function really depends on some key components in a network instead of one single node. Even though in many cases a single node is important, but in many other cases in education, for example, I followed a colleague's works who studied small group work in the classroom, and what he found was 4 different cliques of students collaborating with each other because of their group formation process. And in a different situation would be in the classroom, there could be a lot of students forming friendships, and that could influence the way they will interact in the classrooms. So understanding those small group dynamics is key to our goals of understanding the whole network, or key to understand why some specific students get left out or become a star of these classrooms. So I think studying the middle level that's between the whole network and individual nodes in the network is key, and that's a main goal of this week's work for us. And like earlier weeks in the textbook, there is a chapter that's specifically deal with this topic. And however, I realized this textbook would benefit from some additional exploration of intuition, because in some sections I think the emphasis on mathematics is a bit too strong, and the exploration of intuition, exploration of the conceptual understanding, or so sometimes sociological interpretation of those concepts become a bit thin. So the goal of this video is to kind of really quickly highlight a few key concepts you're going to deal with this week, and so that you can engage with the textbook a bit deeper, or maybe sometimes more easily, and also help you to understand this mathematical computation and help you interpret this mathematical computation in a sociological, in some cases educational way. So let's get started. And what you see here is a demo network I created that where I'm going to use this network to demonstrate a few key concepts. The first concept, if we're going from the top to the bottom, the top would be the whole network, and the bottom will be individual nodes in the networks. The first key concept you're going to encounter this week is called components. And it's fairly simple because the definition is pretty intuitive. That means a component means in every node in one component, there could be a way to reach every other node. For example, you see in the current network, there are 2 different components. The first component, you can see the smaller components, is down here. Let me open the annotation function of the PDF so that you can see I can do some annotation. So the first component, as you see, there are 3 different nodes on the bottom of this network, and so there are different paths for them to reach to each other. And there's a larger component up here with many more nodes. So for this specific network, there are two different components. And I mentioned the way to define it is, for example, if you want to go from this node here to this node here, you can find a path to actually go following this path to reach from one node to another, and so those two nodes belong to a same component. It's fairly straightforward. And however, if we want to add additional characteristic to the network, for example, if this network is directed, because right now this network is undirected. In case it is directed, then the definition of components become more complicated, and you will find out in some cases researchers are trying to distinguish weak component versus strong components based on the direction of the ties. For example, a strong version of a directed network would be considered, for example, let's consider just two nodes, just to get an intuition. If we want to find out the strong components, we need to make sure that ties are bidirectional. So within a strong network, all the ties between in a strong component, a node should always find a path that can reach every other node, and the path has direction. So you can only go, for example, if this tie is in this direction, you can only go from to this direction, but you cannot really go from up the top direction, the top to the bottom direction. So there's a bit additional restraints if you're going to identify a strong component in a directed network, versus in a weak component. The definition of connectedness between nodes is there is a presence of a tie, and without considering the direction of the tie. So it becomes kind of similar to what we are seeing in this undirected network. So if you are interested in those two different kind of definition of components, feel free to find out more by searching online. And I just want to point out there are different definition of components when we're trying to find out components. So in social network analysis, there's a very popular algorithm that will not a algorithm, but many algorithms that try to achieve the same goal of finding out how many components are there in a single network. And this network is pretty simple. There are two components. We can visually even find out, but for some larger, very huge networks, it's usually depend on the computer to find out. So that's the first thing for this video, which is component. And the second thing is, if we find out one component, in this case, there is a pretty large main component for the network. And the next step would be trying to deep digger into this specific network to understand its internal structure. And the reason we're going to dive into this component is because this smaller component down here, it's fairly small, it's fairly simple, so it becomes less interesting for understanding this network, versus the larger network up here. Understanding the dynamics there would be very, very important for understanding the whole networks. So the motivation of doing additional dive-in or additional analysis of components in a network is to find out ways to characterize substructures under a main component, and then try to find out whether there are any kind of local interesting phenomenon we can study. And and for that purpose, there are many different other terms or concepts you're going to read about, and you're going to maybe also play with in this week. The first thing I want to mention is called blocks, or in some cases they are called nodes. And I want to mention again, in social network analysis or in sociology, there are a lot of competing definition of the same term. So you might find out there are many by blocks, different researchers mean quite different things. But here I want to give a kind of our working definition of blocks in a social network. And to define blocks, it's important to first define cut point. And cut point in social networks, it means basically for a component, what we see here, this larger component, one cut point would be if we remove that node, this larger component will become two components. For example, if we focus on this specific node, if we remove it, you can see this larger network become two different networks. So this become disconnected. They become one smaller component up here, and there is another component here. And they become disconnected because we remove these nodes here. And similarly, if we want to remove this node, if you can see here, then similarly they become two different components. So those two different nodes, they become cut points. And after defining cut points, and then we can define blocks. And in social networks or in components in a social network, a block basically means what gets disconnected after removing a cut point, and also including the cut point itself. So this become one block because they are kind of disconnected in a very interesting way, because this node is key and its cut point, and it becomes an independent block. And in the meantime, this part becomes another block. And similarly, what I mentioned, because this node is also a cut point, this is a block, and you could treat this part as another block as well. So so the reason the block is important is there is some kind of interesting local centrality going on, especially with the cut point. And understanding blocks and understanding the specific cut point in blocks become really interesting. And you can try to think of possible application of this concept in your own research. And I don't want to really dive too deep into it. And so that's the first thing I want to mention is blocks, and also the concept of cut point under blocks. And then you're also going to read more about different things to further, especially further narrow down, further leave out some kind of nodes from a component. Because the social network analysis, the process as I see is you go from raw data. For example, you collect a lot of data from Twitter discussion, and then you want to narrow down to some either more dominant sometimes, or more isolated nodes, or in other cases you're narrowing down to a specific group. So the process of narrowing down when analyzing a network is actually trying to filter the network, and some other people use the term slice a network. So it's kind of removing some nodes, removing some edges from the network so that you can narrow down to a specific unit, a specific component in the network, and to support additional analysis, either it's visually or mathematically or qualitatively in some cases. So the process of narrowing down right now is to go from right now the larger component we see to different kinds of subunits of these components, and there are many different terms. And the first term I want to mention is called key cores, and which is also I think covered in the chapter. And the way we go from component to key core is basically to narrow down based on the degree of its nodes in this component. For example, if you want to say we want a 2-core component, then that means we want to narrow down from this component to only keep those nodes with 2 or more degree. And in this case, we see kind of every node in this component has 2 more or more degree. And so everybody remain in this component. However, if we keep increase the value from 2 to 3, we want to focus on 3 core component, then you can see this node and this node and this node, because the degree of them are 2, and also this node, so that they will become removed from this component, and so that we only keep those other nodes with with 3 or more than 3 degree in this specific kind of subunit of the larger component. So this could be interesting. In some cases, you want to narrow down to very more influential people, more kind of core people in a group, so that you can study them more specifically. And so going further, in addition to K cores, which is based on the degree of its nodes, there's another concept called M cores. And M cores, and it's a little bit different, but it's kind of similar to K core. The purpose is similar, it's to narrow down to subunits, but the focus of M cores is based on the links, and it's another word is based on kind of more sociological term, is based on the multiplicity of the connections, and which is oftentimes represented by the weight of the connection. For example, if we want to do 3M core, then that means we want to focus on those edges or those ties with at least a weight of 3. So in this network, actually, what it was, let me see, I want to add some additional information here so that we can talk more about it. Actually, in this network, the weight of a tie here is 5, here is 5, other are 2, this is 1, 1, 1, 1. So if we want to focus on the ties with at least 3, with a weight of at least 3, then we're going to kind of remove this part of the network from this component, and this part become also removed, and other ties under 2, this also become removed. So basically, we're going to keep this part of the network become a kind of 3M core of this larger component. So it becomes another way to narrow down from a larger component into very small, tightly connected, highly important component of this larger component. So I think those concepts could be useful in some cases, and it's again, it's your decision, and to define whether you want to keep first of all, whether you want to use K cores or M cores when you're trying to narrow down, whether you want to focus on the degree or whether you're going to focus on the weight of the connection. And also the parameter you're trying to set, whether it's 2M core or 3M core or 1M core. And also it's informed by usually your research purposes or your understanding of the context, or some other kind of theories you're following. So there's no golden rules for you to follow when you're trying to define or trying to make a decision on which specific technique to use or which value to use. It's more your informed decision, like we discussed in earlier weeks, talking about earlier measures in social network analysis. And again, if you have specific questions or specific discussion points, feel free to post in our forum and we can brainstorm together. And so that's about two kind of standard, very popular way to find out subunits in a larger component. And then if we move on Let me remove the notes so we can talk more about it. If we move on, there's another very interesting and important concept called cliques. Cliques is just like what we talked about, key core or M cores, is another way to further narrow down from the component. And the way it narrowed down is a clique is defined by this way. So in a clique, every member of the clique are connected to each other. So comparing to the definition of components basically mean there is always a way to reach to another member in a component, no matter how far the other member is in the network. Versus in clique, it is every member in the clique are directly connected. So it's become very, it's kind of limiting the distance between each other in the clique, and trying to emphasize the clique, everybody are interacting directly instead of indirectly. So for example, in this network, if we want to look out for some cliques, what I realize is this part become a clique because everybody in this part are connected to each other. However, if you look at the left part of this component, even though those 4 nodes are somehow reachable between each other, for example, you can go from this node in the bottom to the top by following 2 different paths. However, there is no direct connection between them. So this subunit cannot be treated as a clique. So that's the distinction between clique and component. And also, if you want to look a bit deeper, there are many different things going on. For example, those 3, they also form a clique, right? And those 4, they also form a clique because they are directly connected in this network. So there could be many different cliques, and there could be a lot of overlap between cliques in the social networks. And again, it depends on which kind of research question you are trying to answer and which research scenario, which research context you are working in. So I don't want to dive too deep into it. And the best way to learn about how to use them is to look out for some examples, especially from educational literature, where I believe there are many researchers using the concept of cliques, and in many cases using a combination of cliques, cores, or blocks, or sometimes components to serve specific purposes. So if you can find more literature about that, feel free to check them out and share it to the class so we can all benefit from this kind of collaborative learning and sharing. And because clique itself, the concept is really strict, it's very hard to find those really tightly connected cliques. And in this case, this example is special because it's small and it's very well connected compared to some other real-world scenario, where connections are usually less dense and more sparse. So researchers have trying to find ways to rules or trying to reduce the restriction with cliques, and they came up with a few different ways to do it. And the first way to do it is called n-clique. And n-clique, let me just write it down. And the definition of n-clique, it's pretty intuitive, and it's based on the distance. So the clique itself, the strict definition is the distance between every individual nodes, every pair of nodes in this clique is 1. Versus n-clique, you could actually increase that value to 2, so that you can, so the distance between every pair of nodes in a 2 clique becomes maximally 2. So in that case, this part of this component become a 2 clique because the distance are actually 2. And also, however, if we consider this node, and we can this part of this network doesn't form a 2 clique because this node and this node, the distance becomes 3. So, however, if we change the value from 2 to 3, then this forms a 3 clique. So kind of very interesting way to enlarge or try to expand a more strict definition of one clique or clique to a larger part of the network to include more people. However, if the value you can, if you go to, for example, 4 clique or 5 clique, the interpretation of this kind of clique become really hard, because what does it mean to have a distance of 4 and you still, as a researcher, you're trying to understand, you're interested in this kind of clique, because the far you go between two nodes, the less connectivity or the less meaningful the connection become in many situations. However, in some very other kind of situation, you might be able to justify a larger value of the clique. So that again up to you, and you need to make a theoretically informed decision on that. And the Cliques, the concept built directly on one clique, or the default definition of cliques. And however, it add additional characteristic that says, okay, in the very strict definition of clique, everybody need to be connected. However, in a keyplex, we are going to give you an excuse to be not connected with key number of other nodes. So, for example, if we want to look at three-plex, okay, want to look at three-plex, and we want to start from this more established part of the clique, because they are already well connected, and let's see whether we can include other members to this three-plex. For example, if we consider this one, if we think about clique as 3 other members that this node can be excused from being directly connected, then this member could actually become a part of the clique, or the part of the three-plex. And again, this one is similarly could become part of the member, and this one as well. So that's another way to kind of expand, or to remove some of the restriction that a clique would have, so that we can actually capture more local interactions, local members into this analysis. So we could actually analyze more people in some cases. And again, it depends on specific research situation and specific goals you're trying to achieve. And we can, if you have specific research, and we can actually come together to talk more about it in the class. And I think that's enough for you to get started with this week, and to dive deeper into components and cliques, especially under a complete network. And when you're going through the textbook, you're going to check some more specific definition of those concepts, some mathematical computation of it. However, I don't want to really emphasize on those mathematical computation, because because the textbook mentioned bottom down, or bottom up, or top down, there's different kind of ways to do it, and I don't really find those very important in many of this analysis. So if you can, if you find them useful, find those definitions useful, then it's fine. If not, then I think the video give you enough conceptions that you can actually use, and you can actually kind of build upon by exploring specific areas I mentioned. For example, you're interested in cliques specifically, then try to dive into cliques and try and find out how other researchers are using cliques in their research, and then come back to this computational stuff to be familiar with the specific computation techniques. And I think that's more kind of straightforward and easy to follow, instead of starting from the textbook definition, and sometimes I find it really confusing. And I hope that's enough for you to get started. Again, feel free to post questions, and hope you have a great week.